So the topic for today, it's a very big topic to talk about monitoring challenges in polar waters. So today the focus is on logistics, on transportation. So where sea ice is the obstacle, but also the hazard to transportation. And we have a presentation also on the environmental risks. So it's basically to address the risk part, but also how to do planning right in this part of the world. So I'd also like to say that we have a very busy session. We have a keynote speech followed by 6 10-minute presentations. So that means that we have to be on time with each presentation. So the keynote will get 20 minutes, and the rest will have 10 minutes. And my colleague from the Norwegian Ice Service, Penny Wagner, she will keep track of the time and give all the speakers a reminder just to keep this on time. We hope that we can allow for one question after each presentation, but in theory, that should lead to 5 to 10 minutes for presentation and discussions at the end. But last but not least, we have some dedicated space at the lunch area where we can continue the discussion. So I would like to encourage everyone to take part of that and take that as an opportunity for a continued discussions. So, since this is very busy, I think it's also time to get started. So we have a keynote speech presented by Professor Dylan Jones from University of Portsmouth. He has worked on ARCSAR, which is a Horizon 2020 program, and through that study, they have developed a methodology for classification and prioritization of Arctic and North Atlantic maritime safety and security needs. I think that's a big one, so take it away. The floor is yours.
Okay, thank you very much. Indeed, I think you got it correct when you say it's quite a big and it's a wide-ranging topic when we talk about Arctic and actually North Atlantic maritime safety and security needs. The scope of ARCSAR was potentially even broader, but for this speech, I will look mainly at the maritime issues. Okay, so this is joint work between all of the ARCSAR partners and the wider network, really. But the authors here are the same as for a paper that's published that I will point you towards at the end from the European Journal of Operational Research. And they're from our lead partner, the JRCC Norway, and ourselves at the University of Portsmouth. Okay, here's one side that if I was talking to, I'm a mathematician, so if I was talking to fellow mathematicians, I might point out this for context, but I'm sure it's unnecessary for this particular audience, but simply that it gives a pointer to what the European Union was interested in come 2016 and 2017 when they were funding a course research into this topic, particularly that last point there, in that with the melting ice comes increased activity in the Arctic and the North Atlantic, with some issues there, container shipping, oil and gas, military, tourism sectors. So they really wanted to project into the future, have a look at the current state of the art, and do some foresight analysis about what might happen and where SAR and MERS, search and rescue, marine environmental response, needs to go, and what innovations in particular need to take place in order to cope with this expected future expansion. Okay, so here's the ARCSAR project, 21 partner. It originally was to run until 2023 this year, but because of the pandemic will now run until 2024. It contains really quite a wide variety of partners, Quite a few, as you would expect, are practitioners, but also you can see lists of industrial stakeholders, governmental stakeholders, and universities like ourselves at Portsmouth. And its key aims is to address the security and safety threats that will result from the increased commercial activity in the region. Now, when we put the proposal together, there were three key threats that were kind of highlighted. One was if a cruise ship carrying thousands of passengers with a certain age profile got into trouble in the Arctic or North Atlantic waters. The second was a large Exxon Valdez type oil spill happening in Arctic or North Atlantic. And the third one was some form of nuclear incident. And some of you, there were some extensive discussions at a very good session yesterday about a nuclear incident and the nuclear activities in the Arctic. And adding to this, the whole range of what I would call more higher frequency but lower consequence incidents that could happen as well, so not to forget those. So we're focusing on maritime search and rescue. There's the website that you can link into. So first of all, our task was to first map and then prioritise need for INSAR and MER. We did this by a largely, the mapping was a largely qualitative methodology, so we designed a series of workshops throughout 2018 and 19, and then post-pandemic these have been augmented by a further set of workshops, the last of which is actually taking place next week in Ireland, stakeholder workshops. We went into more detail with semi-structured questionnaires. We looked at other projects, set up working groups. So we had an extensive exercise of mapping in needs for innovation, knowledge, research, and collaboration. And this is the end result that's taken from the paper. So we use, very roughly, we use the IMO Polar Code as categorization on a high level. So you can see the 6 categories there, from vessel, life-saving, communication, pollution and incident control, navigation and voyage planning, and personnel training and education. Initially, we were going to put into need categories, so we had 20 different need categories beyond that, but these were again quite diverse. As it's been said, this is really a wide-ranging topic, so we went to 75 different sub-need categories of different needs of innovations that the practitioners were telling us. Okay, the problem then is, again, 75 is a large number to focus on for a single project. So although we can map this as a pointer to what needs to be done and where we need to go in the future, we worked through and came up with some form of prioritization. And here we needed a more quantitative methodology. So you can think of this as a mixed methodology study. So we used pick charts. You might have heard of these, putting into 4 quadrants, things that are possible, implement, challenge, and keep back. So the 2 dimensions on the chart are the level of assigned importance and the level of perceived difficulty of solving the challenge. For this, we didn't go to a full stakeholder workshops. We rather went to further questionnaires and expert opinions via surveys. And we used a technique called knapsack-based goal programming that will give us a set of priority needs that is designed to A, shape the future ArcSAR project, and B, inform other projects and other innovation agendas and policy agendas. So the obvious thing you might think is to maximize the overall level of importance of all of the sub-needs, but there's no point having everything in the communications category and, say, ignoring vessels. There has to be a balance across these 6 categories, and the temptation, of course, would be to go for low-hanging fruit, but in other words, the short-term needs, but we wanted to try, looking forward into the future, we wanted to try and have a balance between long and short-term needs. And so what you can see there in this rather probably hard to pick out all of the legends, but just to give you an idea, these are the geometric needs of all of the difficulties and the importance. So the dotted line is the geometric mean of expert opinions, or their average. So you can see them divided into things that are should be implemented fairly soon on the top left. They have high levels of importance but are judged to be relatively low difficulty. Things that are still important but high difficulty are in the top right. And then of lower importance are the two other categories, either difficult or not difficult. So mostly we'll be sampling from those top two quadrants and trying to get a balance between the left and the right. All of this, what was the results of this? Oh, by the way, you can see all of the different experts that we consulted for the different categories at the bottom there. What's the conclusion? Well, here you see, again, I will refer you to the paper for a fuller detail of all of the sub-needs, but basically what you see here is the list of chosen priority sub-needs. Now, they're the ones that we are focusing on driving forward in the immediacy of the ArcSAR project or recommending to be pushed forward. The ArcSAR project is a CSA, using European Union terminology, so it's a collaboration and support action. It's not a research project in itself, and it's not even an innovation project. So it's designed to get collaboration going rather than to do all of these fundamental pieces of research on each of these categories, because that would take a very large budget and a longer time. So some of the key words that you can see there, technologies, yes, you would think about, when you talk about innovation, there's a kind of mindset that talks about technologies, but a lot of the innovations, the word that dominate technology is actually standardization and collaboration. Now, this was a key theme that came through all of the workshops that we looked at. Liaisons with hospitals, liaisons with communities. We had an event up in Svalbard that I know some of you were at here. A LiveX to look at how the community copes in the case of a large-scale incident. AI is a theme that's coming through, such as analytical tools for ice and route condition forecasting. Some of these have already led to further projects funded by the European Union, such as the AI ARC project for assessment of risk and using AI in the Arctic for vessel tracking and monitoring. Okay, how is this going to be used in and beyond ArcSAR? What you see, those photos, by the way, is the event that I mentioned up in Svalbard, where there's a evacuation of a vessel. So we will have a series of policy briefing papers coming out of ArcSAR. We are looking at the way, because we've organised several TTX, tabletop exercises, and LiveXs, we look at the way that we can link the science and the technology innovation agenda to how they link into these exercises as well. Obviously, the innovation uptake agenda is important, and we've run through most of our events, but one thing that I would like to highlight and welcome you to is the final conference. That in this we will highlight over a couple of days in much more detail than I'm able to do in a kind of keynote speech here. It will highlight all of the innovations and the work that has taken place in ArcSAR and look forward to what comes after, beyond ArcSAR. So you're invited to that conference. Okay, so to wrap up, what have we learned during the ArcSAR project? Number one, to echo the introduction that I was kindly given, it's a wide-ranging topic. The Arctic, ANA, the Arctic and the North Atlantic. I think that there's been real benefits from using a mixed methodology, so an extensive qualitative mapping of stakeholders, and then a more quantitative mathematical sort of prioritization process to try and weed out what is important or highlight what is important. Slightly dubious saying what is important, because it's all important in the safety agenda, but what kind of makes the top of the relative importance list. This is a natural, what I would call a multi-criteria decision-making problem. I would do, because that's my main field of expertise. But what I mean by that is that there are conflicting ways in which we can measure success here, long-term versus short-term, and then sustainability, economic, environmental, social sustainability when we look at solutions versus technical criteria. And all of this is taking in the background of increased activity. The other thing I should caution about is that the prioritization I gave was of course a snapshot, a static point of view of around about 2021. From a process between 2018 and 2021, whereas technology and advances in technology, and indeed the geopolitical situation, as we're all well aware, is not static, it's dynamic. So consequently, that priority list needs to be revisited and updated as any piece of work would need to be. Arising topics, as well as dealing with more security issues that have been probably best placed in other sessions. The use of AI. I mentioned the AI Art project, and what was missing is drones were hardly mentioned in about 2018 and 2019, but come the LiveX and come this year in the stakeholder workshops, they're quite a large topic, the use of drones in SAR, in MER, in rescue. Okay. One thing to note, just to finish off, we think about product innovation, but a lot of it is about process innovation. Standardization was mentioned again and again, between disciplines and between territories. So that will be the topic. I know it's a bit late to invite you now, but there is the third ArcSAR stakeholder workshop happening in Cork, Ireland next week, where we will be looking at the theme of standardization, and all of these will be written up as reports about what we find. So hope that gives you an overview of the ArcSAR project. There's the reference there for anybody who wants to look at the issue further. Thank you very much.
Thank you so much, Dylan, for setting the stage for this session. So I was wondering if there are one or two burning questions. You'll probably know that this is a hybrid event, so we have to use microphone for questions and comments. So please feel free. Then I have a comment or a question. So can you elaborate a little bit about what is intended to follow ArcSAR? Because you mentioned that the project will end in a year from now. So, and I see lots of good work is coming out, and I think it would be wise to bring at least parts of it further. So maybe we have some thoughts and considerations on that.
Indeed, that will be a topic of discussion at the Reykjavik final conference. So there's a couple of possibilities here. Certainly, some of the overarching Arctic organisations have shown an interest of taking some of the deliverables and some of the products, such as the process and the innovation arena where we list all of our innovations. So they will not disappear. It's an open question at the moment, but safe to say that something will follow ARCSAR. The results will not be lost, but that's ongoing discussions at the moment.
Okay, thank you. All right, I think we will move on to the next presentation because now we have set the stage. So now it's time to hear about the planning component about moving at the sea in polar waters. So I'd like to invite Mr. Martin Gerstel Bjørndal from the Norwegian Defence Research Institute to give a presentation on median routes for safe maritime travels. Take it away.
Thank you. So I'll be describing a method for creating safe routes based on historical AIS data. So such routes are important because the deviation of a good route is associated with an elevated risk of grounding or collision. So not really a route deviation case, but still, to illustrate, in 2009, such a grounding happened in close to Langesund in Telemark County. This was a severe oil spill. So it had rather devastating effects on the short term to local marine flora and fauna. So a grounding incident is an obvious safety hazard. It's an environmental hazard, but it also inflicts enormous costs. So the goal of this project has been to design, develop, and implement an accurate route planner, and this is collaboration with Kongsberg Nordkontroll and the Norwegian Coastal Administration. So, to set the scene, ship traffic in Norwegian waters is increasing. This causes a need for more automated surveillance tools, just in order to be able to keep track of all vessels in our areas of interest. And an accurate route planner is a nice tool for this because it also provides us with, if accurate, then accurate estimated arrival times. So this is of great importance to government in order to oversee the ship traffic and prevent unwanted incidents. It's an advantage for defense due to potential security risks, and for industry because accurate ETAs facilitates good traffic planning, traffic optimization, less fuel consumption, harbor visit scheduling optimization, and so on. So this is again associated with reduced costs. And this is sort of a proof of concept, right? So we've taken a fair bit of AIS data and created routes from a start to an endpoint, and made a set of historical voyages that we use for route planning. So over to the actual method. This is a set of routes, and a route can be represented as just a sequence of points, eh? So it has a geo and a time stamp, at the very least, and potentially other data as well. So a set of routes is a set of point sequences. And when you have a set of point sequences, you can divide them into segments, and you can sample one point from each segment from each route. This provides a set of point clusters. So this is six segments with 6 corresponding point segments. And once you have a point cluster, you can do quite a bit of statistical inference on that cluster. You can do spatial statistics, right? So this is the median point in orange, and connecting the dots, you get what we in the following refer to as the geometric median route. So the orange dot is the geometric median point of each cluster. This is a nice product in itself, but what we are actually outputting from this procedure is one of the historical routes, and it's the one historical route that is the closest in geography to the median route. So by your chosen metric, in this case, what is known as the Fréchet distance for you mathematicians out there, the reason why we're doing this is because this is an historical route. It has been sailed, and it is therefore guaranteed to be safe as long as you don't include garbage data in your in your original data set. So a few complications that may arise is physical obstacles. In this case, it's actually quite simple to overcome, because this is the point cluster, the yellow points, and then you can just do a sub-clustering by, again, your chosen clustering algorithm. And you can create a geometric median per sub-cluster. And with this, these 2 points, you can create a geometric median route per sub-cluster. So this would result in 2 geometric median routes, and then 2 possible planned routes for the vessel. We would also like to have some kind of measure of how much discrepancy between a vessel's location and a vessel's route that is considered to be okay. We would like to have sort of a safe zone. So the red dots in the top images are the border of the subcluster. So anything that exceeds this red point is considered to be off route or off the safe zone. And overlaying the 2 bottom images, we get, this is the ferry track that crosses Boknafjorden in Rogaland. And we see that the 2 directions of travel separates quite nicely. So to conclude, accurate route planning is a nice case as long as the volumes of historical data is sufficient. So you can do it for individual vessels, you can do it for vessel groups, or you can even do it for all vessels. But it's a good idea to have some sort of categorization, either on length or on vessel type, because they do exhibit special behavior or different behavior. Splits in the route is not really a problem because it's data-driven. So when you have a set of routes that creates multiple paths, then you can just do a subclustering. Again, given sufficient data volumes, that's something that's actually quite easy to get hold of. Bad weather may cause such route splits. Bad weather can cause vessels to go closer to land or in between islands. And the point clustering provides an implicit safe zone that you can use for creating route deviation alerts and alert the vessel traffic service operator if you want to. So thank you to the partners, and that's it for me. Thank you.
Any questions to this nice presentation? Yes, one here.
Thank you. My name's Kelsey Frazier. I'm from the Ted Stevens Center for Arctic Security Studies. In the state of Alaska, we've been toying with geofencing for route planning as a means to help navigators avoid maritime or marine populations that are procreating, moving in and out of waters. Do you have anything like that, or have you considered that?
We have considered it by extracting polygons from map layers and stuff like this. It's not implemented in this, but we have a separate route planner that is, this is dependent on the fact that somebody has been going this distance before, right? So somebody has traveled from A to B. We have another route planner that is supposed to be universal, which can plan a route from any like wet node in a graph to another node at sea. And this is the case where we include this, or suppose we would include that component, because then we can we could penalize the graph traversal based on the location of the node that could possibly be inside such a no-go area.
Makes sense. Thank you.
Yeah, we can take one quick question.
Thank you very much. My name is Jamie Anderson. I'm from Oil Spill Response Limited in the UK. I was wondering if your data took into account vessel draft or size, and if you changed any of the routing methods because of it?
Implicitly, because you would, I suppose, you would divide on either single vessel, like a regular runner, if you want to, of interest, or a vessel class, or a set of vessels, say between 40 and 80 meters of length, that would have, I don't know, not the same draft, of course, but yeah, you could, because it's data-driven, you could for sure, but not explicitly, no. All right, thank you.
All right, thanks very much. I think it's time to move on to the next presentation. So, that's a presentation still on ships operations, but now in polar waters, and a look on how the climate has changed over several years, and also how risks have been addressed. So I'd like to invite Jean Holloway to the stage, and give her presentation on climate change and evolving risks for Arctic maritime navigation. So the floor is yours. Thanks.
Thank you. Hi, everybody. I'm Jean Holloway, and I'm a postdoc at the University of Ottawa working with Jackie Dawson. And today I'm going to be talking about work that Jackie and myself, along with Alison Cook, who will be giving the presentation following mine, actually, so stay tuned for that, and Adrian Nicol. So we've worked together on this data set as a team, and I'll be talking today about evolving risks for maritime operations in the Arctic, but with great detail about the Canadian Arctic and how climate change and risks are changing over time. So this is the time series of Arctic sea ice extent in September based on the long-term satellite record, and that solid black line there is the observed record. So you can see that that's been decreasing rapidly over time, and is expected to continue to decrease in the future under all warming scenarios. You can see that on the right side there, left side. And the Arctic is expected to be seasonally ice-free, which means less than 1 million square kilometers in the summer months by as early as 2050 for some of these projected scenarios. And some studies have shown that the Barents Sea is expected to be ice-free relatively in winter months as early as that as well. So we are expecting less ice in the Arctic over time, which will create opportunities for ship operations and other things, as well as risks and challenges. This is year-round projections for the open water vessels for the 3 major transpolar shipping routes. And I just wanted to highlight that all routes are expected to be open for at least part of the year in the next 2 decades. And you can see the sort of broadening of the plumes there over time, which just indicates that there's a lengthening of the open water season for vessels. So yes, more opportunities. But however, we heard some interesting talks this morning in the sea ice session, or the sea ice side meeting, about how variability in ice conditions is really changing. The ice pack in the Arctic is highly mobile now. There's still ice present, and I wanted to highlight here, even though the Arctic is expected to be seasonally ice-free, there will be ice present for decades in what's called the last ice area. And this ice is going to be advected southwards in the Canadian Arctic, into the Canadian Arctic archipelago and also into other areas in the Arctic. And so, there is still hazardous ice present. And the example on the left side there is so typically, historically, ice arches in Nares Strait would prevent this, import of ice south, but those don't form every year now. And so this is an anomalous year, which you can see the sort of red and orange colors are this thick multi-year ice that's moving southwards. And by the last panel at the bottom corner there, you can see multi-year ice as far south as Newfoundland, which is in June, which is really atypical. So some of our results for the Pan-Arctic, you can see here that shipping across the Arctic has increased. So this is AIS data from 2012 to 2020. And you can see that it's almost tripled. And areas where it's increased substantially, Baffin Bay, the Greenland Sea, Barents Sea, Kara Sea, they're all labeled there, Bering Sea. So yes, there's been a great increase in ship traffic, particularly later on in the record. Fishing vessels are the most prevalent overall, followed by cargo vessels, passenger vessels, and tankers. And the Norway has the highest amount of traffic, so you guys are number one, yay. Followed by Russia and Iceland. Yes, and so compared to some economic zones, Canada actually has relatively low traffic, but you can see here that it has been increasing rapidly over time. So the top panel there shows that it's quadrupled since 2006. There was a relatively stable period from 1990 till then where traffic sort of remained the same, but then increased rapidly. And that's particularly true, you can see in the bottom panel there, for vessels with little to no ice strengthening. So those are things like yachts, pleasure crafts, so yachts, sailboats, fishing vessels, and though that is in sort of these light peach colors. And you can see especially that increasing after 2006, a rapid increase in those vessels. And that's particularly interesting, especially because I mentioned that there's still this highly mobile, hazardous, thick ice that's present in the Canadian Arctic archipelago. And this is an example of a sailboat that had an incident with ice in 2018 and sunk, and they needed to be rescued. And we've heard a lot today about how those types of those rescue operations and things are quite challenging in the Arctic. And in Canada, at least, that type of emergency response is it's not this. We don't have much in the Arctic. They have to come up from down south, so it's quite an endeavor. Allison, who's speaking next, will go into detail about how the methods we use to calculate risk, but we use the IMO Polaris method, which we also heard about an overview about this morning in the shipping or the sea ice side meeting. So we use the Polaris method to calculate risk in the Canadian Arctic. So I wanted to highlight that 96% of operations that occurred since 1990 occurred in this normal category. So that's the gray bars on the right side. But if you look just at the operations that occurred in elevated or high risk conditions, those have been increasing in the sort of most recent time periods. So since 2010 especially. So different types of vessels show different patterns and risk, both temporally and spatially. So here I'm just showing the 3 vessel types that traveled under the sort of higher risk conditions. So those are fishing vessels, passenger vessels, and pleasure craft. So you can see that on the right side, the number of ship position reports in these sort of elevated risk conditions increases over time for all 3. But if you look on the left side, the percentage doesn't change much for fishing vessels and passenger vessels because the total number of those vessels also increased rapidly. So the overall percentage doesn't change much. But that's actually different for pleasure craft, which is at the bottom. So you can see there that the percentage actually also increases, and these pleasure craft actually are the sort of fastest increasing in risk in the Canadian Arctic, and they're also the fastest growing sector. And again, those are actually all of the fishing vessels and pleasure craft that especially, they're typically non-ice strengthened. So they're operating in these higher risk conditions. So this is an example of what we can do with sort of spatially looking at these risk, higher risk conditions. And so this is for fishing vessels and for pleasure craft since between 1990 and 2019. And so for fishing vessels, you can see that typically they operated in sort of Baffin Bay and Davis Strait area, and that they stayed typically in that area over time, although they have moved a bit farther north in the later time periods. And the sort of the red and yellow dots there are the elevated and high risk conditions. And so you can see an increase in those dots over time, especially for the high risk. But they're typically located in Baffin Bay and Davis Strait. And pleasure craft is probably the most interesting overall. So you can see in the top two panels, 1990 to 1999, there was no pleasure craft operation at all in the Canadian Arctic. And then it's rapidly increased, especially through the Northwest Passage. And that's where all of those sort of higher risk incidents were occurring in that Northwest Passage area. So just to conclude, we've seen ship traffic increase across the global Arctic, and including in the Canadian Arctic, although at slower rates and less overall than in other areas. In Canada, 96% of vessels have operated in normal operating conditions, but the number in these elevated or higher risk conditions is increasing over time. And especially in areas like Franklin Strait, Lancaster Sound, and Frobisher Bay. And we've got a report available online, and we're writing a manuscript right now where we go into great detail about these things. So if you're interested, let me know, and I can send that to you. And just wanted to highlight that as the Arctic continues to become more accessible in the future, Alison in the next talk is going to talk about shipping season lengths and how those are changing in the Canadian Arctic. But so we are expecting to see, risk change, maybe more accidents, and, especially as vessels are operating in these high risk conditions. And so yes, that creates challenges, but more traffic also creates opportunities, and I just wanted to highlight that as well. So it's about management and how we work forward as a community to operate safely in these conditions. And with that, I will take any questions.
Yeah, thank you so much. I would suggest that we move on to the next presentation because I believe that we only had the first half, and your colleague Alison Cook will probably give us some answers. So Alison is with us online, I believe. So Alison Cook from the Scottish Association of Marine Sciences in the UK. And the presentation is about the variability in safe operation shipping lanes in the Canadian Arctic. So, Alison, the floor is yours. Welcome.
Hi, thank you very much. And I'm sorry I can't join you today, but it's great to be able to speak to you and follow what Queen says, because we work together and it's always exciting. So I'm looking at the variability in safe.
So, I'm not sure what's happening. Okay, obviously we have a technical issue here. We see you, but we cannot hear you. So would it be better if we move on to the next presentation? We have some background music.
strange. Very strange.
Okay, so we are ready to go?
Can you hear me? No? No?
Yeah, yeah,
Okay.
we can hear you. So the floor is
Oh,
yours. Thank you so much. Welcome.
Oh, okay. I'm back. Okay.
Yeah, sorry about
I don't
the
know what that
inconvenience.
music was. It wasn't me. Okay. All right. I'll try sharing the screen again. Okay. And I hope you can see my screen now. Okay, let me just do that. Yes, okay, thank you. And sorry I can't join you. And thank you, Jean. And we're working together, so this does tie in very well. So I'm looking at the variability in safe operation within the Canadian Arctic region based on historical data from ice charts. And I'll run through how we did that. I might have to be a bit quick. But so as Jean explained, there has been an increase in shipping, and there's also been a decrease in sea ice area since 1990. And what we see though is that the detrended correlation is low, so year to year it doesn't exactly match up, and we need some answers there. So sea ice decline, yes, are the routes actually safer for travel? That you might think they are, but are they? We need to look into these things. What's causing the differences? Are shipping seasons getting longer? And where are the regions that are most at risk for ships with low ice strengthening? So we tried to address these things by using two different data sets. The really key one, and is fantastic, is provided by the Canadian Ice Service, sea ice charts. We use the weekly charts that show the different types of sea ice and concentration, age, and extent. In addition to that, we use the polar cloud classification of the ship hull strength, and this ranges from PC1, very, very strong ice strengthened ships, to PC7, these types of ships, which are more medium ice strength, and then anything below that value is weaker. So 1Bs, for example, might be pleasure craft, and then sometimes you obviously have no ice strengthening. So combined, these two different data sets show some key results, and this graph shows the work that I did classifying every ship that's been in the Nordreg zone since 1990, and what are the normal ice strengths, what types of ships are going there. So PC7, medium ice strength, there are a large number, but 1B, the weaker ice strengths, are the most common ships. So this is the method we use, which is Polaris, Polar Operational Limit Assessment Risk Index System by the IMO. And it's a very, very good standard system that using sea ice conditions that are present in the region in combination with the ice class of the vessel gives you a risk index value. And from this and the ice concentration, you can calculate the risk index outcome, RIO. And what I wanted to do was use all the historical charts to look at the RIO values that indicated normal operation. So regions that were safe, or well, safer and less or no risk to ships, just to identify what are the regions that have been used for normal operation. And here we have Mike Brady converted all of the ice charts from each year into what we're using, defining as shipping seasons. So a season is the number of weeks, maximum 37 weeks, that a vessel of a particular ice class is able to travel under normal operation. And so for every year, we have this as season length grids, 1 kilometer cell size. And I did this for 4 different polar code classes. So not for every code, but for these examples, strong, medium, weak, and non-ice strengthened. So we have a really good, large data set now, but we wanted to focus on the Northwest Passage first of all, just to see, this is a really busy area, obviously, and separated into these 3 different ice strengths. You can see the number of ship tracks that have changed over time. So PC7, the medium ice strength in particular, has increased in number, and so have the weaker ships. PC3 have decreased, and that's because a mine on Cornwallis Island has ceased to run. So there are now far fewer ships going in of that ice strength. But anyway, we wanted to look at using the ice charts, what were the season lengths for ships during those times. So I took a mean for 5-year intervals since 2007, when the ship ice chart data began. And what I've done is use the main shipping routes through the Northwest Passage. If you run your eye along the graph left to right, that is from west to east along the red line, the main route through the Northwest Passage. And you can see the change along the route of shipping season length. And Larsen Sound and Peel Sound are the shortest season length. And they are popular areas for ships to go, but the season length is quite short, and it's becoming slightly shorter as well. But this is probably the more interesting region, the Northwest Passage in the north part. Viscount Melville Sound, as you can see in the graph on the lower left, that's a very short season, and the pink line is the most recent years, so it shows that the season length is actually becoming shorter. And the same in McClure Strait and in the East Beaufort Sea region, it's becoming quite substantially shorter, which was a bit of a surprise for me personally. Anyway, I wasn't so familiar with the shipping season. I suppose we assume that sea ice decreasing means longer seasons, but actually in these regions they are shorter. And in Prince Regent Inlet, that is an area that has longer season lengths, and it's not changing much or even becoming slightly longer in that region. The Northwest Passage northern regions, we looked at these areas in particular year by year. Is it a constant, steady decrease in season length? Well, there is a lot of variability, but the main part of the year where the season length is decreasing is in the middle part. So in the summertime, the number of weeks that the season for safe shipping is actually becoming shorter. And again, we might be surprised, but actually there is an explanation here when Jean mentioned this, which is the multi-year ice that's coming down from the north, and it's actually entering into that passage, McClure Strait and Viscount Melville Sound. So we know that the multi-year ice is causing more hazardous conditions to ships in that region, and the seasons are therefore shorter. This is from Stephen Howell's paper recently, which does show that. And I must be quick here, but the further work, we need to look at these other ship strengths. We know that non-ice strengthened ships obviously have shorter seasons of normal operation, and we want to know where those regions are, and therefore show to maybe yachts and pleasure crafts and tourist vessels where it's still not safe to go for if you have a weaker ship. So the summary, we've converted all the ice charts into the risk index outcome maps, and we can then work out the shipping season lengths from these. We've shown where the areas in the Northwest Passage have normal operation in the northern part of the Northwest Passage. And we call these choke points, and that's where multi-year ice accumulates. And it helps us become more aware of risk, and multi-year ice recovery continues to be a main factor in preventing the safe travel. And people need to be aware of this, and what does this mean for the future viability of the Northwest Passage? So these are questions, and hopefully our results have shown some answers at least to this, and methods that can be used elsewhere. Okay, thank you.
On. Thank you. Thank you so much, Alison. Interesting presentation. I think the two presentations actually supplement each other quite well. So we are a little bit under time pressure, but we can have one burning question. At least I have one. I was wondering if you can see any developments in the variability from year to year in the data from 2007 to 2021. The reason for asking is that for ship operators, the presence of ice is not the real challenge, but that's the variability from year to year, because the planning side is so tricky. So can you see any trends in the data? It's a fairly short time series, but I'm just curious.
Yes, you're right. It is a short time series, and we would need to take it further back in time a bit. And there are ice charts to do that, but they don't have quite such a good number of weeks per year to do that. So no, we're not seeing a very specific trend year to year. We just do see a lot of variability, and it's only in those regions, Mickler Strait and Viscount Melville Sound, that we see that trend in the last 15 years. Elsewhere, there does seem to be a lot more variability. I didn't show some other graphs that, particularly in Peel Sound, there is a lot more variability. So I think more work needs to be done in looking into that to work out why some areas are showing more variability. Certain years stand out, like 2018, there was less sea ice. Sorry, there was more sea ice, so fewer ships were able to get through. So particular years do correspond well with what we see in the climate change data as well. So there is a connection there, but more work needs to be done. Yeah.
Thank you. I think we have to move on. So the next presentation will focus on the human element of navigation in polar waters. So I'd like to invite Ms. Hui Xu. Is that correct? Yeah. From the Arctic University of Norway here in Tromsø. So and you'll be talking about the need for simulator training to improve maritime safety in a changing Arctic. Because one thing is to have the skills and ability to navigate safely in these waters, but also to maintain and develop. And we heard earlier this morning that there is also some focus that some waters are, for a long time, be ice-free. From time to time, the ice coming in, so that creates a whole different set of challenges for the mariners. So, but let's hear more. Thank you so much.
Hello everyone, my name is Helena. So the professor has already introduced our topic, so I move on to save time. This is the introduction. As the climate changes, the Arctic warming more than twice as fast as the rest of the planet. Arctic air temperature were about 3.4 degrees above average in 2019 and were the second warmest since records began in 1900. The Arctic region is undergoing significant change due to global warming, which has led to increased access to the ice-free Arctic and the commercial activities moving northward. So that's the background of our study, and more because as vessels access the Arctic area, they may encounter broken ice that is drifting and moving on the waves, which pose a significant challenge for bridge officer. The oil and gas industry is also moving north to extract hydrocarbon resources, and installations in the Barents Sea are vulnerable and to drifting ice and iceberg. These events can cause oil leakage, severe damage to the vessels, and potential fatalities. So our research question is here: what are the key challenges facing bridge officer and the vessels in Arctic region, particularly with regard to broken ice and drifting icebergs? How does the use of simulation training in a ship simulator impact the preparedness of bridge officers to handle the navigational challenge in the Arctic? How can the effectiveness of the simulation training program be evaluated? So this is the objective of our study, to develop a simulation training program that takes into account a realistic scenario and prepares bridge officer and start to handle the challenge of the changing article environment, to evaluate the effectiveness of simulation training program in preparing bridge officers and staff to handle the challenge of changing article environment. So we have and this is our method we are going to use in this study. So we will, a simulation-based training program will be developed and implemented with a sample of group of bridge officers and staff. The training will include a focus on dealing with an emergency situation in a towing task in the Arctic area and will be carried out in a ship simulator. A simulation scenario design will be developed by a team of experts in the field of Arctic navigation and include the most important elements and the features that are critical for preparing bridge officers and staff for the navigational challenges in the Arctic region. The decision-making skills of the participants will be evaluated after the training using a proposed assessment tool. Data will be collected through and after simulation training. Questionnaires will be utilized. So this is the proposed customer decision quality rating system. We developed this tool based on the decision they made. We ask the question based on decision, and answer by answer this question, we give the quality of the decision and give the such rating. And the future work is we are going to do ice management simulator training and development of the simulator training involving drifting iceberg in waves. Ice simulator training should be part of operation of Arctic oil and gas facilities. So this is the example of we have done an example of complex scenario training experiment. We develop a complex simulator training experiment. The experiment involved two tugs towing a barge through narrows. The experiment demonstrates that UIT has the capacity to develop complex simulator experiments. The development of the experiment was carried out during the spring of 2022. The experiment was tested by several groups of students have different levels of competence in using the simulator. It is suggested that this case shows the effect of the level of familiarization with simulator training. Even a low level of familiarization with simulator training led to good decision making. The example demonstrates the potential effect of preparing simulator training for handling ice and also for towing icebergs. So this is the experiment we designed. In this experiment, we ask the participant in two and two as a team to towing our object here. So it's here like this is object. That's two boats they are towing, and this is conducted near the Tromsø area through the narrow water, and this experiment conducted in a very good weather. This is where usually towing operation conducted. So we introduced two failure induced in this experiment. And so also this is the result. This is the result from our study. We used the NASA TXL rating to evaluate their perceived workload and the physical mental performance rating from themselves. Also we we find out they feel relative high stress during this operation, and that's why we come out a lot of variable options of decision during this experiment. This is one of the creative decision from one of the participants. He decided to go through in a very narrow, which is dangerous, but she's a success, so that's also can be option. This is the result from our experiment. This is options for all this decision made by the participant during the experiment, and we have the analysis of the consequence of the decisions. So based on this, we gave such a rating, and we get the decision qualities. So the discussion and the conclusion part is that the results show that this naturalist decision-making model is suitable for the analysis of participants' decisions. And I just want to highlight that the training program is necessary to prepare bridge officer and staff for challenging the Arctic air environment and improve safety. Experiment and knowledge are important for handling emergency situation effectively. So here is the reference I used, and thank you very much.
Yeah, thank you so much. I'm afraid that we have to move on, but I'll just remind everyone that during the lunch break, there's an opportunity to get much more details, because we have this sidebar in the lunch area where we can ask questions, etc. So that's just to remind everyone. So we still have 2 presentations to go. So now we will move into another aspect of Arctic operations, namely the environmental component, the environmental assessment. So I would like to invite Senior Advisor Øyvind Rinaldo from Kystverket here in Norway to give a presentation on assessing environmental risk on monitoring of ship accident frequency and acute pollution. So the floor is yours. Thanks.
Thank you very much. Hello, everybody. The Norwegian Coastal Administration, I'd use NCA for short, put 3 new tools to help assessing and mitigating risk resulting from accidents into use in 2022. Ship accidents, that is. Even though there are 3 separate tools, they make up a whole. In this talk, I will only focus on the risk assessment tool, ICE-risk and ENVI-risk. Shortly, what they are. The ICE-risk is a computer tool for calculating and visualizing the risk of a spill or loss of lives resulting from a ship accident. ENVI-risk is a computer tool to calculate and visualize the environmental risk resulting from spills after a ship accident. The aim of these tools is to have a comprehensive and quantitative basis for making contingency plans and setting levels of response and mitigation to handle acute pollution from ship accidents. Both tools have been used for the first time in a big analysis in 2022. Even though they are designed to assess and mitigate risks for the NCA, there are other possible users and uses, and I'll get back to that later. Let me tell you what makes these tools different from what has been done in risk assessments earlier. ICE-risk calculates accident probability and frequency very differently. Instead of using a traditional probabilistic method based on statistical accident frequencies and sail distance, ICE-risk uses detailed AIS data to map traffic and the actual risk situations. AIS stands for Automatic Identification System, originally designed as an anti-collision system. Ships send out AIS message as often as every second and up to 3 minutes apart. The messages contain an ID, the position, speed, bearing, status, and other information connected to the voyage. Ship data for each actual ship and voyage is collected, and we use that to set the ship type, ship size, and tank capacity, and so on. We use actual weather data and sequence data for the exact date and time and place for the ships that we are analyzing. Even the near misses that otherwise are very hard to detect are detected by this system. The consequences of the ship accidents on the far right can be acute pollution in the form of a crude oil or oil products spill. In the future, other spilled substances will be added to. Loss of lives is used in navigational safety assessments. A little more about what sets ISO risk apart from the other risk assessment methods. As I said, ISO risk use actual voyages, the ship's positions, and a safety zone approach to calculate accident frequencies. A big ship has a bigger safety zone than a small ship, and a fast ship has a bigger safety zone than a slow one. The same applies when looking at groundings. If a ship is too close to the shore, a higher grounding probability is calculated. In a critical turn, speed, time of the turning, and the distance to shore is used to calculate the probability of a grounding. Drifted grounding is calculated by using actual weather data and a drift model. Calculating frequencies of foundering, that's when a ship breaks up because of the force that it's subject to. And fire and explosions still rely on statistical data. We use international statistics for this type of accidents. NRISK picks up the result from ISO risk and uses a spill point, oil type, and amount of oil as starting point for oil drift modeling. A large number of drift simulations gives us a good picture of how the oil will spread and how much oil will hit each grid cell in our analysis. Again, actual weather and sequence for the time and place is used. Now we are getting into the environmental consequences. We use sensitivity or vulnerability data for seabirds, marine mammals, and marine life in the water column, down to the species level. Each species has a vulnerability to oil, and we use this to set the impact that the calculated oil spill and drift has. We use the traditional formula frequency multiplied with consequence equals risk to calculate the environmental risk. All results and data are available in a 10 by 10 kilometer grid, and the ship accidents are available in a 1 by 1 kilometer grid. And the time resolution is 1 month for the results. Let's see if this, it's not running. Okay. Yeah, there it is. While you watch the animation on the screen, I'll tell you how I think ISO risk and NRISK and or other tools like this may be of use for monitoring impacts of changes in human activity in the Arctic. While you watch, just look at the intensity of the color. Higher intensity, higher environmental risk. Don't try to see what the exact level is. The NCA uses these tools to assess and mitigate risks, risk of oil spills resulting from ship accidents. In a changing Arctic, the tools play other roles too, can play. Changes in activity levels in the Arctic will often result in a change in ship traffic or ship traffic patterns. Decreasing ice extent or other climate changes, demographic changes, new or obsolete industries, new legislation, moving fisheries, and a lot of other changes will show up in our data. Some of you know the Mosaic project, the cruise with a Polarstein drifting across the Arctic Ocean. That showed up in our analysis. So that could tell you something about the sensitivity of this. In general, more activity leads to a more or higher risk. So it's monitoring the ship traffic. It's fairly easy, and we can do that, and already do that. Very much automated. Monitoring wildlife or vulnerability is not quite that easy. It is a longer process and absolutely not automatic. Monitoring changes in industry and society is also not automatic, still possible, and can be part of how we use tools like this. Assessing and monitoring risk levels is an important task, but mitigating the risk is even more important. For the NCA, mitigating of environmental risk can be done through, for instance, contingency plans, like we do, the right oil recovery equipment, competence, and exercises, and also through legislation, awareness, and knowledge. But the absolutely best mitigation is to do everything we can to avoid the accidents happening. We don't really know what other risks might show up by studying these data, but of course, if there are any, they will show they need another type of mitigation. But our tools like the one we have, they can be used to other purposes than they were originally designed for. IC risk and envy risk are just two tools in our sea of initiatives to assess and monitor risk. And it's a very complex field with many layers. This is just a few of them. We can see that using these tools for other purposes can be of help. And of course, we would also like to have others have a look at these tools, see if they can help them in their analysis. So if anybody wants to investigate this, please feel free to get in touch with me.
We have time for one very quick question. Penny?
I would like to know, can you explain a little bit about how it deals with the sea ice information? Because I think in the previous session we talked about there's different types of suite of products. So what types of information does it normally use?
For now, we don't use sea ice information at all, actually. That's one of the things we have to develop in the future. But that's what we want to do in the coming year. So we need to know more about the ice conditions, physical, how the ice reacts to a ship, and how the ship reacts. So that's one of the things we have to do.
Yeah, thank you so much. I would like to invite our last speaker to the podium. So I'd like to invite Dr. Knold Kaufmann to give a presentation on the Arctic paradoxes, on the Arctic trends and risk and safety development in Svalbard waters. So take it away. Thank you.
Yes, thank you very much. I'd like to acknowledge my project partners here. This is work that is part of 2 From Center projects, and which we are, especially in the Sudarko project, now developing further. Background for these perspectives, somewhat different perspectives on risks are, of course, the sea ice decline and increased access to the Arctic waters lead to large expectations of new activities in different sectors. These activities we know now from these sessions take place in challenging environments, and there's an increasing focus on risk and implications for safety. And as Øyvind just said now, more activities is higher risks, and we need to have different perspectives on this risk development. So objectives in the paper that we are developing now is to achieve a more comprehensive understanding of risk development in the Arctic, explore the role of the polar code and its consequential risk paradoxes, which I'll come into, and outline new areas of research that we will follow up in the Sudarko project. So risk is most often understood as the product of the probability of an accident and its consequences. It's a traditional approach to risk, and we've seen now that there are many more comprehensive approaches to risk, to understanding risk development. It's a product of several interrelated dynamic factors, each with their own uncertainties. And in our paper, we have a look at these different elements, where we look into activity trends, operational conditions, regulatory frameworks, and information and infrastructure, which is very broad, which includes search and rescue resources, but also med-ocean services, communication services, etc. Each of these have their uncertainties in how they develop further, and each of these also has an effect on the other, and thereby impacting the overall development of maritime risk. So we see risk management also as a process of sense-making based on available information and uncertainties on each of these different factors, and of course also including situational awareness and previous experience when operating out there. We've seen many of these figures this morning, but I just want to briefly stand still here. We see that on the right side, ship days in Svalbard waters are increasing. You see a huge peak in the summer of 2022 when cruise tourism was increasing again after a pandemic. And you'll also see this pandemic influence in the dip down there in the figure on the left side. We know that in Svalbard waters it's mostly fisheries, cruise tourism, and vessels in the other category operating there, which includes research vessels and search and rescue, for example, surveillance vessels. There's limited activity beyond 81 degrees, and we see overall an increasing number of ship days, expanding seasons. We know that the cruise sector has expanding shoulder seasons and expanding geographical operational areas, especially again where expedition cruise tourism is trying to find new frontiers. Now, the Polar Code is is this framework, as we have been introduced to, of coal-based risk governance, and it was entered into force in 2017 and relates to construction, design, training, information requirements, safety and human safety and environmental risk aspects are included there. So it sets different objectives and performance expectations, which means this goal-based risk governance means there are these functional requirements, but the responsibility to reach these goals and to implement measures to reach goals is situated with the operators. And just two examples that we will draw further on in our work is this requirement of being prepared for at least 5 days survival. This is a minimum. That's one of the requirements. Another requirement is to obtain information about relevant mid-ocean conditions, sea ice conditions, weather conditions, for example, about hazardous conditions which relate to the particular ship category. It could be minus 20 degrees or a sea ice coverage above 10%, for example. But we also have heard now that there are many implementation gaps to the Polar Code, also relating to these two requirements. First, it's difficult to establish operating limits, and there are some unrealistic functional requirements, like this being prepared for 5 days survival. The SIREX exercises of the past years have shown that this is, with the current technology, not possible, especially also taking into account that there are, on these cruise vessels, the type of persons on board and their health situation could not be those who survive longest in these conditions. There's a lack of data for voyage planning. There's a lack of data about conditions below minus 20 degrees, for example. These cannot easily be forecasted. There's a lack of forecasts we know now about sea ice conditions. So it's really hard to actually do this. So we know that there are implementation gaps, that it's really risky to operate out there, that operators are responsible themselves. This is a discussion, especially here in Norway now. Should there be additional risk management measures? For example, limitation of number of persons on board. There's this topic about higher insurance costs for remote areas. Is that an issue that could be implemented? Stricter routing requirements based on what we know about weather and mid-ocean conditions in different regions, increased training requirements, or this obligatory twinning or buddying policy where, for example, expedition cruise vessels need to be 2 and 2 in an area in order to be able to save each other. We are, I'll finish with 2 sets of reflections. One, reflections about risk paradoxes as a consequence of, this increased awareness of risk in the Polar Code and this self-responsibility. On the one hand, we have 3, so not on the one hand. We have this impact paradox. We see that ship-level activities are allowed for which we know that the consequences can be large for many, and there are few areas in society where so many persons are involved, where such a level of risk actually is allowed. So that's a paradox. There's this exposure paradox. This twinning or buddying policy, which is a good idea, that risky operations will actually be safer when more operators are willing to take those risks, to be together out there at the same time and in the same area. Due again to this self-responsibility and the limited resources out there. Then there's a service paradox. We've been hearing this morning as well about the many modeling efforts and introducing new services to tailor needs of operators out there. There's a lot ongoing. Decision support services. On the one hand, of course, these increase control. On the other hand, they also might expand the operational possibilities and push the frontiers, which in turn might increase risk. And I think this is something that we all have to be very aware about. So I'll finish this up with some new areas for inter- and transdisciplinary research that we're really working on now in the Sudarko project, in an interdisciplinary project with stakeholders involved as well. We'll have a stakeholder workshop in April about these topics. We'll explore the strategies and expectations about future maritime operations in the Arctic, including, getting insight about drivers and barriers of future fishing activity and cruise operations in these areas. What can we expect? And we'll map the outer limits of high Arctic operations, combining AAS data, mid-ocean data about the distance to SAR services, and trying to identify critical areas and seasons and maybe connect this to these new routing measures. Would that be a possibility? Look into historical data about how often is it actually happening that the 2 vessels are operating in the same area to, is this buddying principle feasible? And to find out what are the threshold parameters actually for rescue operations. Thinking about these hazardous conditions, how often do operations take place there? And what are the outer limits for search and rescue operators to be able to assist when in need? And finally, we'll try to understand the feasibility for these different possible regulations to prevent accidents and reduce risk in relation to this work that we're doing. So thereby, I'll leave 1 minute before lunch. Thank you very much for your attention.
Yeah, thank you so much. Now that lunch was mentioned, I would suggest that all questions and comments are addressed during lunch because that's about to take place now. So unfortunately, we have lots of balls thrown into the air, and it would be nice to have some panel discussions. But again, I would like to suggest those to continue during lunch. So we have had some fantastic presentations this morning, focusing on the logistics of Arctic navigation and transportation, but also the risk management, also the environmental part of working in those areas. So I would like to remind you that this is part one of a session that's continuing tomorrow at 11 o'clock. So around the same topic on challenges for monitoring and modeling the Arctic waters. So today has been on the logistics. Tomorrow will be on observations. So today has been very interesting, but I believe tomorrow will be even more interesting. So I think I'll close the session. I think we should give all the speakers a big hand. So thank you. And lunch is served.